Thanks. I'm Jesse Burns from ISEC Partners.
And I'm Peter Eckersley from the Electronic Frontier Foundation.
And we're here to talk about observing the SSLiverse. So,
this is a project that both EFF and ISEC have been working on thanks to some very generous assistance from the NMAP Foundation. What we've done is we've downloaded a set of all the publicly visible HTTPS SSL certificates, and we've built a big database of them, and we're looking through to see what interesting things we can find.
There's just a little overview of what we're going to talk about, why we need the observatory, and then some of the results we found. We'll talk about conclusions and future work at the end.
Surprising that. So, as you've probably realized at this point, HTTPS is a pretty important protocol. We do almost everything over the web, and the only hope that the web has to not get completely owned by everything is to encrypt itself and use SSL. And HTTPS relies on certificates in order to ensure that the website you're talking to is actually the website you want to be talking to, and not some person in Bulgaria who's just put up a fake site that looks a lot like the real one. And the key component of this infrastructure for checking who you're talking to are certificate authorities. They're these people who go around and they sign certificates saying this public key really belongs to google.com. This public key really belongs to microsoft.com. This public key really belongs to your blog. And as you should imagine, anytime you hear the word authority, you should question it. The best answer to authority is transparency and accountability. So we decided to apply some of that to the existing state of the CA world. Now, there's a reason why we're doing that as well. And that is, there's been a growing amount of concern that the way that SSL uses certificate authorities is inherently problematic. There's a growing amount of work of this kind. Chris Segoyan and Sid Stam recently did some, but then last year there were 3 instances in which we observed attacks against HTTPS that were a result of mistakes or oversights by certificate authorities. Now, one of those was as simple as saying, we'll give a certificate to anyone who can show that they answer administrative email at a domain. And here's a list of 20 email addresses at that domain, root, admin, administrator, postmaster, etc., etc. If you can answer any one of these, then we'll give you a certificate. And of course, out there on the web, there are some webmail providers who haven't reserved all of those names. So, but there are more sophisticated attacks. So there's the attack by Sotorov et al., where they observe that some CAs use MD5 as part of their certification process, and then fail to randomize a serial number. And so they were able to find an MD5 collision and also predict the serial number so that they could make the MD5 collision work in practice against a CA. And when that happens, it completely breaks HTTPS for everyone. There was another example where certificate authorities were found to be signing certificates that had /0s, 0 bytes, inside the names of websites. And then, of course, although the certificates use Pascal strings, so it's okay to have a 0 byte in the middle of the string somewhere, browsers use C. And so they'd interpret that /0 as the end of the string and add a different semantics. These attacks, unfortunately, may pertain only to one CA. But there are a lot of them, and the security you get for HTTPS is only as good as your weakest CA. And so it starts to matter how many of them there are and what they're really up to. And in a sense, our project, which we're going to report on today, or at least initially report on, is to try and find out who these CAs are and what they're up to. So we download everything and see what we can learn from the results.
All right. So our observatory has a little bit of infrastructure. Actually, we didn't need a lot of stuff to do this, but we did need a little patience. So we had 3 low-end Linux servers with only 2 gigs of RAM each, a good shared 100 megabit network connection with people that were supportive, NMAP with poor timing settings, some Python code, and some time. So we ran this thing, and we did all the analysis, or most of the analysis, on a single year-old i920 CPU with a fast disk and a lot of RAM, and 2 little laptops. So tying together OpenSSL, a MySQL database, and lots of little Python scripts. Currently, we unfortunately, our community contribution is vaporal, but we intend on making a distribution of our database. We have a little problem where we've uncovered some vulnerabilities and we need to finish all our disclosure before we can do that.
Yeah, so put it another way, hopefully in a few weeks we'll have a website up at EFF, or a page up at EFF where you can download the entire data set that we got here and see if you can improve on our findings. It'll be a big BitTorrent download, and also some little web forms where you can say, enter a domain and see, okay, these are all the certificates that were observed in in weird, shady parts of the internet that claim to answer for that domain. So the first thing we did, we said, well, we need to know where the SSL servers are. And so some people there have been some pre-existing projects that have gone looking for them by, say, compiling a list of the top 1 million names and resolving them and then going to see if they answer over HTTPS. We took a sort of more brute force approach. We contacted every IPv4 address on port 443 using NMAP, sent it a SYN, and if it came back with an ACK, we just jotted down that fact. We did this with these little work units of the form, you know, number.star.star.number. It's a bit like the work units you use for SETI at home, except instead of observing the sky, we're observing SSL. You need to do that so that if something crashes halfway through, you don't have to start the whole scan again at the beginning. So you have the work units you've done and the ones that are still remaining. And then once we've seen an IP address reply, we then jot down that and come back later with a little Python script that will send an SSL hello message and just record the reply that it gets.
One of the things that's kind of nice about this moment in time, it's 2010, it's perhaps the last time that you can reasonably take this approach. We're running out of IPv4 address space. IPv6 is 128 bits. We're not going to be sending SYNs to each of those. And there's these new technologies that are improving the internet, like server name indication, SNI, and SPIDey and other protocols that extend SSL and make it so that when you say hello to a server and ask it for its certificate chain, you have to know who it is that you want to talk to before it tells you who it is. That will make our lives harder.
Yeah, another way of saying that is currently virtual hosting doesn't really work for HTTPS. It does work for modern browsers, but anyone who's deploying a website needs to support, you know, IE7, IE6, all these legacy browsers. And until those are gone, you can't do virtual hosting and SSL. And so in a sense, we're relying on that in order to make this work.
Extraction of certificates. So maybe what we could have, what we could have done would have been easier if we'd have used something off the shelf. But what we decided to do was write a custom client with Python and construct. And part of the idea there was that we might have bugs in our understanding of the TLS protocol, but we want the bugs, the parsing errors, to be bugs that we could understand. That was really important to us. So we didn't have to implement all of TLS in order to do this. Just these little parts I've outlined here. And that allows us to detect failures. We went off the RFC definitions, and then we just had to kind of debug it with Wireshark and some test cases. Turns out that the RFC is a little ambiguous here and there, and you really have to dig around to find some places that work. But once we did that, we were able to collect SSL certificates without actually having to do the key agreement part. So that's very efficient. You just say hello, and it sends back some bytes, and you drop the connection when you see that they've given you everything you need to reconstruct their whole certificate chain. You don't even need to do any key agreement stuff at all. So we can't.
No crypto math. Basically.
Yeah, no crypto. So it's nice and quick. And then if we make a mistake, we can go back after the fact and reanalyze.
So at the end of this process, we're left with a big pile of X.509 certificates. And as an aside or a reminder, it's worth dwelling on what X.509 actually is. It's a standard, or at least a recommendation, that was promulgated by the International Telecommunications Union, the sort of the international club of telcos, in the 1980s, back before the web existed and SSL existed. And the general advantage that the protocol has is that it's amazingly flexible and extensible. It's completely abstract, completely general. You can do anything with it. These are also its disadvantages. And so the fact that it was able to be kind of retrospectively bolted onto the web is maybe a testament to its flexibility, and also perhaps we might have been better served with a lean, narrowly defined way to do encryption for the web, but instead what we have is this complicated infrastructure that has a lot of security features that are hard to understand, especially when you start to take the intersection of all of them. So we have these things. We need to parse them.
And there's no real right way to parse X.509 certificates. I mean, there's ways that they say to do it in the specs, but one of the things that we're really interested in is how maybe two different implementations might look at an X.509 certificate and see something different in there, like the great example of those nulls. So we didn't, want to try and write it the right way. What we did was we decided to do it one of the wrong ways that was fairly easy and gave us a lot of data fast. And that was to use OpenSSL's X.509 text pretty printer and then to parse that. And we've actually experimented with some other ways of doing this because obviously there's information that shows up in certificates that your C client might not be the best thing to see. You can use a Java server or a certificate parser. You can write your own code very similar to the OpenSSL verify command or the OpenSSL X.509 command. All that source is available. It's easy to see how they're doing that and make your own little tweaked versions. But ideally we want to have different views of the certificates, and then we can agree on fingerprints, which is just the hash of the Dur encoded bytes of the certs, which should never change, and we can join all that together and conduct our analyses to see maybe which views are different.
So in order to analyze this data that we just parsed, we put it all in a gigantic set of MySQL tables. And then as we noticed interesting questions that we wanted to ask, or interesting properties we wanted to examine, like the relationship between domain names. Like there might be many certs that in different ways claim to be relevant to a particular domain. You want to build separate tables to capture those mappings. And then once you've built this big MySQL infrastructure, basically a question that you want to ask about the state of SSL turns into a fancy query you can write. And we have a couple of examples of these later on in the slides. And then once we're ready to publish this data, hopefully you can all go out and write your own queries against this data set. And in a way, this approach is it gives us the flexibility that you need to handle all of the crazy internal complexity you've got inside X.509. And then the first thing that we did with this set of tables was try to work out which of the certificates was valid. And that turned out to be quite tricky. It's very important, and there are some more, but perhaps not all of the gory details later. But what we found in general was, okay, there are 16.2 million machines on the internet, at least when we scanned, that replied on port 443 with an ACK. And then of those, if you actually looked at what they said back to you, 10.8 million or thereabouts of them gave an SSL response. The others, who knows what they were. They were random bytes that they came back with. And then of the 10.8 SSL handshakes, 4.3 or so million of those had a valid SSL cert chain. The others were self-signed, expired, invalid in some way. And then if you look at the valid ones, a lot of them are the same chain repeated on multiple IP addresses, so you get down to 1.3 million valid leaves if you want to throw away the repeated chains.
Which is very close to the number of valid certificates. So there's a few extra ones in there we'll talk about later. So a little crash course on what it means to be a valid X.509 certificate chain. When you put up a website running HTTPS and you just serve up the certificate you got signed by a CA, that'll often work because the trust root chain is already, that chain, the subordinate CA that signed your browser, or your certificate is already present in the browser. Usually though, you send back a trust chain. So you send a couple of certificates back, and then the browser orders those and figures out if this chain really maps back to a trust root. The trust root is what grants you the authority. So This is a really important process, so I just want to give you the dirty version of it. When you check a link in the chain,